Thank you.
So I think we can move to our last speaker, Sebastian Netter, who will present iDRILL, an instrumented drill for lunar volatile prospecting.
Thanks for the opportunity to present and also to the whole team. I'm Sebastian Netter from OHB, from the Mechanisms Department from Munich, Germany. And I'm going to present iDRILL, which is an instrument to characterize and analyze volatiles in the regolith of the lunar surface. And maybe a short note to this picture here on the first slide. We didn't drill into lunar regolith simulant here, but in wet beach sand. And it looked quite nice, and that's why we put the picture here. Okay. Then, first of all, what was our motivation and the background? Well, for the in situ resource utilization, you need to know which resource you're going to face on the lunar surface. And therefore, our instrument is going to detect and characterize volatiles in the lunar surface and on shallow subsurfaces. And we want to go with near lunar landing missions. We don't have a flight yet, but we hope we will find one soon. And we want to go to the lunar polar regions, and we want to have a versatile and adaptable payload because we want to be adaptable to the mission we want to go with. Because of this needed versatility and adaptability, we also have a demand on our instrument for low resources in terms of mass, volume, and power. And what is also beneficial is an end-to-end lunar sample handling and analysis chain, which means basically we want our instrument should be able to take the sample and also analyze it and characterize it. Possible candidate missions are the LSAS mission, LUFMI, LUFMI-X, or iSpace P, but basically any missions which is going to the lunar South Pole regions. I guess Chris also already mentioned some. What is the science case between this development? Well, water and water equivalent hydrogen was identified in permanently shadowed regions and also in higher latitudes. And stable water ice is present in the polar areas in depths less than 10 centimeters. Apart from that, the water desorption from regolith requires a temperature of up to 400 Kelvin, and from other elements, temperatures are required from up to 800 Kelvin or even more. And so we see that this the scientific literature shows that or indicates that there is an abundance of water on Luna, but yet we don't have any ground truth data, and we want to collect this with iDRILL. And the working principle behind this mechanism is, well, we have a hollow drill shell, which you can see illustrated here, and you have then the ceramic heating rod in the middle. And this hollow drill shell is then drilled into the lunar regolith. And when the desired depth is reached, the heater is turned on. And after more or less 90 minutes, 70% of the sample reaches a temperature of up to 400 Kelvin, which is necessary to release strongly chemisorped water. And more or less 5% of the sampled regolith reaches temperatures of 807 degrees or more, which is necessary to release the solar wind implanted particles. Those volatiles then go up through this orifice into the ion trap mass spectrometer, where they are characterized and analyzed, and their composition out of elements and isotopes and molecules is determined. In addition, pressure sensors in this instrument provide an information with respect to the pressure and therefore give an indication of the abundance of volatiles in the analyzed sample. A short overview of the design. Our assembly can be separated in 3 subsystems. First of all, we have the probe head, which is basically this whole system, which consists out of the launch lock, the mass spectrometer. Here in the back, you can also see the electric motor, which drives the hollow drill shell. The housing and the drivetrain, the instrument section with the pressure sensors and the ceramic heating rod and the drill shell. The second subsystem is the linear actuation unit, which basically provides the linear feed of the drill. And then the third subsystem is the back-end electronics, which is installed on the governing system. Those whole 3 systems provide an adaptability and a modularity of the system. So we can either be mounted on a rover, a lander, or also on a robotic arm. For example, on the robotic arm, the linear actuation unit is not necessarily needed, and therefore can be left. Some information on the design where we are coming from. The development started in 2009 by the consortium of OHB, TUM, which is the Technical University of Munich, and OU, the Open University of the UK. We are funded through the DLR and the European Commission's Horizon 2020 program, and we wanted to build a compact and low mass system with high adaptability, which we reached through the modularity of the system, and this end-to-end sample and analyzation chain, which is basically analyzation of the lunar regolith without sample transportation. Here we can also see a prototype and a design of an earlier phase, and this is the latest phase. And this prototype provided TRL5 with also simulated tests with lunar conditions. We already conducted several tests with lunar regolith simulant, whether our expectations were fulfilled. And this first test is with respect to penetration forces and torques. As you can see, it is exponentially dependent on drilling depth. And also it is very dependent on the speed ratio. Speed ratio means ratio between drilling speed, rotational speed, and feed. And as you can see, the drilling, when the rotor is drilling faster, then it's moving forward. There are much less forces exported, but also equally as less torques. And third point is that those two are very important control parameters, because exported forces and torques need to be counteracted by the carrying vehicle and are therefore also limited by it, or a certain threshold shall not be overpassed. Since we tested this in Earth gravity, the results are conservative, and we reached a drilling depth of up to 12 centimeters. But under lunar conditions, drilling depth of up to 20 centimeters are possible if the regolith is not too dense. Another test we conducted is with respect to the cross-contamination. We decided between two different scenarios or types of contamination. One is transfer of granular material, the other one is transfer of volatiles. The granular material cannot be avoided completely, because you can't prohibit any adhesion, or you can't prohibit that no adhesion at all is taking place, but you can drastically decrease it by rotating the hollow drill shell while you extract the drill. You can see this also in the diagram to the right. The upper one is without rotating while extracting, while the lower one is with rotation, and you see that the particle amount is drastically reduced. But in general, the granular material contamination is not that critical due to the order of magnitude between sample and the residual volume. The other contamination aspect is the volatile cross-contamination, and to reduce this, this is done by heating the drill once it is extracted, and by heating it, the volatiles found in the grains, which are adhesive to the drill shell, are released, and those volatiles can then escape through the opening of the drill. Yeah, regions of flexibility of our mechanism are, for example, the mechanical interfaces. As I already said, if you are mounted to a robotic arm, you don't need the linear actuation unit, for example, but also if you are integrated in a rover or a lander, the position of the mechanical interface between the linear actuation unit and the lander can be adapted. That is not a problem. Also, the drilling depth can be adapted by the stroke of the linear actuation unit. Another point which allows flexibility is the launch lock. For example, when you have a robotic arm, you don't need a launch lock like we have, but a launch lock where you can where you place basically the hollow drill shell in a kind of nest to hold it in position will also provide this launch lock functionality. A fourth point would be an additional vision system. This was already foreseen in an earlier phase, but not requested for iDRILL. That is why it is not implemented here. but it would increase the science potential. And obviously, you can manage the harness routing differently. And in conclusion, the design is based extensively on a tested breadboard and on significant heritage with exploration missions, for example, in ExoMars. The required functionalities and performances can be provided, and it is highly adaptable to candidate missions through the means I already described with the modularity and flexibility. So in the end, I want to thank you for your attention, and if there are any questions left, please feel free to ask them, and I hope to be able to answer them. Thanks.
Right on time. Thank you. So we have one question from Julie Klein-Heinz. Sebastian, have you tested or done thermal analysis on your volatile capture method to show the volatile will not be instead drawn down to the cold regolith beneath around the drill? I'm
not the engineer who did the thermal analysis, but I can ask a colleague and ask the question by mail if necessary. And my contacts are on the next slide on the bottom right side. Yeah, I'm happy to help by mail. Thank you.
That was the only question that I can see. So thank you. I think we are, so yeah, that was the end of the session.